So what we're going to talk about is narrow sense heritability. Now imagine you have this chicken strain, right? And you have an average of 100 eggs and an average of 50 grams per egg. If you want to improve it, what you do is that you split it up into two sets, right? You have one set where you have a lot of egg counts and set B where you have a lot of egg weight. And then after this, what you do is you self-cross this set and you see what its F1 generation looks like on average. And the same thing goes for set B. And then you finally cross those two F generations to get an F2 generation. Now, all these have different number of eggs and different number of egg weights. But what we want to figure out is what is the narrow sense heritability. Now, if I'm going to denote narrow sense heritability by Hn, right, this is going to be calculated by the selection response, which I'm going to mark with R, divided by the selection differential. Now, what is this difference? Now, the selection response is the change in the F1 generation to the parents, right? After we already selected a set A. So say like select set A is not the average set, essentially. It's a very shifted set towards one end or the other of basically the parent strain, right? We chose a set that had a lot of eggs. So the selection response is basically what we get once we self-cross that set. And the selection differential is basically the difference between set A and the parent set, right? And so there's a lot of different things we got to calculate the narrow sense heritability. We got to do it for set A for the egg count and set A for the egg weight, and same thing for set B. It's egg count and it's egg weight. But we're not going to do that. I'm just going to do it for one of these, and you can apply the same exact process for all of them, right? So for the selection differential, it's basically a difference in set A from the parents. Over here, we have 150 grams, right? Or not 150 grams, but rather 150 eggs chosen, or 150 eggs that are produced on average in set A. Now the difference from that between the parents is 50, right? Because the parents have 100, and we take the absolute value of this difference, right? We get 50 eggs changed. Now, 50 eggs production difference. Now, when it comes to the selection response over here, we have F1 generation only produces about 120 eggs, right? Minus the 100 eggs that the parents make, and this gives us 20. And so when we divide 20 by 50, right, this gives us our narrow sense heritability, which is 0.4, which shows us that, like, basically we have a possibility to change the F1 generation by selecting a set that is offset. Basically, the set is not in the average. However, since it's 0.4 and not 100%, what that means is there is a lot of environmental and other genetic factors that are not additive, like dominant and recessive relationships, right? That are not allowing us to perfectly change what the F1 generation looks like. And you can provide this, you can do the same process again and again for all of the other factors. Now, if we were to continue doing this selection process, right, what do you expect is going to happen to the narrow sense heritability? If I'm going to keep repeating this process over and over and over again to get like a narrow sense heritability like the 5th time, right, what do you think the number is going to be? Well, it's definitely going to be less than 0.4. And the reason that happens is because the genetic variability is going to get less as we keep doing it. As we keep doing the selection change, this essentially the selection differential over here, we're going to get more true breeding sets, right? And then the amount of genetic variability that's going to be is going to be very minimal, and any variability that's going to be left is going to be from the environment and other factors like dominant recessive factors. Now, what happens when we cross this F1 generation with the F2 generation? Well, we get this F2 generation that's better than both, right? And why is this better than both? Well, sometimes you have something called heterozygote superiority, right? And what is this heterozygote superiority? Well, one example is with sickle cell anemia, right? With sickle cell anemia, say the dominant allele, HA, right, is no anemia, right? And then the recessive allele is going to be our sickle cell anemia. If you have only one allele from the dominant and one allele from the recessive, which is sickle cell anemia, you have a mix in your blood cells. Some of your blood cells are normal, right? And some of them are sickle cell. Now, what this heterozygote basically phenotype does is that it allows you to have a resistance to malaria. People who are homozygote dominant for the regular blood cells will essentially die from malaria if they contract it, more likely. And the people who are homozygous recessive for the sickle cell anemia, right, they're going to die because their cells are basically all sickle cell and they can't carry up as much oxygen as they should. And so when you're heterozygote for this, you actually have a superior phenotype, and it allows you to be better than both the other strains. And so this is what happens when we cross over here these two these two chicken strains. We actually get a hybrid that's even better. And so that's what heterozygous superiority is.